Welcome to another new microeconomics video lesson in this blog dedicated to game theory. In previous videos, we defined the concept of Nash equilibrium in pure strategies, but we show that sometimes there were games where there wasn't one, such as in heads or tails game, for example, or rock, paper, scissors. For those types of situations, in this video, we are going to introduce the concept of mixed strategy and the generalization of the Nash equilibrium in mixed strategies. A mixed strategy for one player is the probability distribution over some or all the available strategies for this player. Given a set of strategies for player I that we usually call S sub I, a mixed strategy is a probability distribution over the set of strategies or the strategies profile, and we are going to label it as P sub I. When someone plays a mixed strategy, it means they choose randomly, giving each strategy its respective probability. Note that a mixed strategy in which a single action receives the 100% probability, that is, this action is played for sure, is called a pure strategy. This is what we previously called simply a strategy in previous videos. Now we are going to see 4 different examples of mixed strategy for the rock, paper, scissors game, which, as we saw in previous videos, doesn't have a Nash equilibrium in pure strategies. For example, one mixed strategy would be playing rock with 80% probability, paper with 15% probability, and scissors with 5% probability. Another different mixed strategy would be playing each strategy with equal probability, for example, 1/3, or playing rock with 40%, paper with 0%, and scissors with 60%. Finally, another example would be playing scissors for sure. This is the pure strategy scissors. Suppose that players in a game can play mixed strategies. In that case, we can define a Nash equilibrium in mixed strategies, such as the vector of mixed strategies or the strategies profile, one for each player, where each strategy is an optimal response or the best response to the other strategies for this profile. Note, since every pure strategy is a mixed strategy too, this definition of equilibrium includes the one we have already discussed in previous videos. When is a mixed strategy a best response? When it maximizes the expected utility for one player. Therefore, a Nash equilibrium in a mixed strategy is a set of probability distributions over the strategy sets of every player in the game. To understand this, consider the following. Given any vector of mixed strategies for the other players, any mixed strategy for player I defines a lottery. So we can determine the available consequences as well as their respective probabilities. With this, we can calculate then the expected utility of that mixed strategy, as we saw in the first block of this course. A mixed strategy for the player I would be the best response to a vector of mixed strategies for the other players, if it maximizes players I's expected utility. The concept of a mixed strategy is important because it can be proven that under very general conditions, there is always at least one equilibrium in mixed strategies. This is known as Nash's theorem. This does not always happen when our analysis is restricted to pure strategies, as we saw with rock, paper, scissors game. To conclude with this video, let's look at an example of how to calculate the Nash equilibrium in mixed strategies. For it, we are going to use the following coin toss game or heads or tails game. Recall that if player 1 plays heads, the best response for their opponent is to play tails and win 1, but if player 1 plays tails, the best response for the opponent would be to play heads and win 1. The same holds for player 1. If the opponent plays heads, they will play tails, and vice versa. The best response is always to do the opposite of whatever your rival does in the game. Therefore, note that no pair of strategies would be simultaneously the best response for both players, so known as equilibrium-less in pure strategies. Now, let's apply probability distributions to each strategy for each player to convert them into mixed strategies. To do this, suppose that Q is the probability that player 1 plays heads, so 1 minus Q will be the probability of playing tails for this player, while R would be the probability that player 2 plays heads, so 1 minus R will be the probability of tails for player 2. The names you use for the probabilities associated with each strategy don't matter. With these probabilities, we can calculate then the expected utility for each player, and suppose that they must be indifferent between both strategies, heads or tails. So for each player, we set the expected utility of heads equal to that of tails. For player 1, the expected utility of playing heads would be 1 minus R, while the expected utility of playing tails is minus R plus 1 minus R. Setting this equal and solving, we get R is equal 1/2 or 0.5. In a similar way, for player 2, the expected utility R minus Q plus 1 minus Q and Q minus 1 minus Q. So, getting equal and solving, we get again that Q would be equal 1/2 or 0.5. This means that the equilibrium for this game could be that each player must play each strategy, heads or tails, with a 50% probability. Note that the probabilities do not have to be equal for both players. In this example, they are because the payoffs are symmetric, according to the matrix shown. Finally, we can visualize the Nash equilibrium in mixed strategies by graphing each player's base response functions as a function of the associated probabilities. In the attached graph, which corresponds to other example extracted from Espinola Redondo and Muñoz Garcia's book, but has the same outcome as the coin game, we can see that the solution is indeed the intersection point of both functions, which in this case would be the midpoint of the probability square, that is 0.5 and 0.5. That is the result of the Nash equilibrium with mixed strategies that we are using in the heads or tails game. In following videos, we are going to learn about how it works when games are not static but dynamic.